So on the topic of histograms then, I'd like to talk about the so-called limiting distributions, because the outstanding question I think about histograms as they sort of show us patterns in your data is, I guess, what is the ultimate pattern supposed to look like? So the histogram really, if we're doing it right, we'll say something about just the ultimate pattern that we'll get. And by ultimate, I mean as follows here. You can sort of start going with a limited data set the way we've done here. Say you had a few data points, and even like the 22, like this might be 22 and 23 and 24 and 25 and so, and maybe we had, you know, one down here at 23 and a couple here at 24 and maybe none here and a few at 25, and so you can sort of put whatever you want. Maybe this is 1, this is 2, and this is 3, you know, that kind of thing. But the question is still, is this really it for the data? You know, is this just the best the pattern's going to get? Because in this histogram here, I'm not really seeing much of a pattern per se. The one that we did earlier by hand, you know, I don't know, maybe there's a little pattern in the 24 and the 26, and even if I go back to the computer examples here, back in Mathematica, you know, I have a couple histograms. I'm not sure that there's a pattern I'm willing to conclude anything about yet in there. And so the issue then with these limiting distributions then is you'd really like to be in a situation here where capital N, which is the number of data points, the capital N here, just becomes very large. In other words, you have a lot of data. Okay? Now I know that's not always possible, and in the case of the limiting distributions technically is when n goes to infinity, and so what that happens is when you get a lot of data points, it gets very large like that, then basically I'll just sort of say in a very non-technical way, everything, and again I mean everything in terms of the pattern, settles down. And what I mean by settling down here is that if you look at this word settling down here, if you look at this histogram here, there's still a lot that can happen as we start throwing more and more data points sort of in our histogramming machine. You know, if you imagine your data sort of like a big input to this here, and you just sort of like another x sub I, you just keep feeding them in there. You know, maybe this bar will grow a little bit and this one will grow, but maybe this one won't grow very much, and maybe this one will grow. And maybe if you do that after n goes to infinity, maybe your histogram would be something like, you know, like this. And as you keep throwing data points in, it just doesn't change very much, and so you could maybe conclude that this is the dominant feature or something like that. I'm not very sure, but that's what we mean by these limiting distributions. So let me go back to the Mathematica just for a second here and say, okay, it's really easy to sort of examine this idea of a limiting distribution, getting a lot of data, because I can just tell the computer to generate more data points for me. Instead of just 10, let's go up to 100. Okay, so we'll get like 100 data points there, something like this, okay? And so as you can see, this may very well be an experiment you did where you've got more and more data points. You know, we can always compute the standard deviation and the mean, and as you probably guess, even in the case of these limiting distributions, these numbers aren't going to change very much more either. As you go, you can always plot the data and get more. You know, it doesn't really help, I don't think, just plotting like that, but there's definitely more, okay? It doesn't help, they look similar again. But then, of course, the fun part here is when we make the histogram of them now, because we have many more data points. We have 10 times the data points. So we really start seeing what happens to these bars. So let me just press the return here and see what we get. See? Now you sort of have something that looks more like a limiting distribution. And in fact, it sort of looks almost bell-shaped now, right? Not so much out here and here, and the bars tend to grow as you get in there, and so there you've got it. And we can look at data set number 2 also, where it looks different now. And they are different data sets. This one's starting to look bell-shaped. This one's starting to look relatively flat. But that's the idea of the limiting distribution. So let me just show you what I mean. Let me go back up once again here. I don't know if you saw that. Oh my gosh. Okay, there we go. See, that one looks kind of flat. This one looks bell-shaped. This one looks kind of flat. So let me go up and, you know, why not? Let's generate 1,000 data points. And I'll put a semicolon after it so I don't need to see all the data. And I'll change this to 1,002 and a semicolon after that because I don't need to see all the data. Let's just see if these change very much. See, like 24 and 1.9. Yeah, a little bit. About 24 and 1.9. These right here, 24 and about 2 or so. Yeah, not very much. You know, I don't expect to see very much in here or very much in here either. You know, they just sort of, well, I don't know. Maybe I'm starting to see some features now. These seem to be clustered around 24. These not so much. Okay, I think I'm starting to see that now, but that's, again, an advantage of a lot of data. And if I go up here to look at the histograms then, 5, remember this is 1,000 data points. Yeah, look at that. And look at how nice this one looks too. So we're definitely seeing some differences in the data sets. This one is definitely looks like a Gaussian or bell-shaped data. This one looks like it's more uniform. And you can see what I did at the very top of my code here. The first data set here are normally distributed data sets. The one and the second one are uniformly distributed data sets. And so you can definitely play around with things that way. And I just think this is great fun here. And you can also mess around with the number of bars in histogram. Like I said before, if I can find a good spot to stop. Yeah, there we go. Let's change the number of bars here maybe to 10 to really make a smaller bin width, smaller category. And you see a beautiful Gaussian start to develop out of our data there. Normal, let's even go up to 20. Look at how nice that looks. So we will avoid this because we don't like these gaps, but I can really see a nice bell-shaped distribution coming here, which tells us something about our data. And we can do the same thing down here as well. Let me make this 20. So a few gaps in there and things, but generally speaking, it looks like each data point is equally likely, as is always the case in these uniform distributions like that. So that is what we mean by limiting distribution. A lot of data points that start to reveal the real structure of what this data looks like. And so in the next video, I'll just give you a few relations in the limiting distribution, and we will be done.